Looking back over all the material that we covered in this course, it's pretty clear that the concept of fields has played a central role in our understanding of electromagnetism. At the start of the course, we used Coulomb's law to introduce the concept of electric fields. Later, we introduced the concept of magnetic fields using the Biot-Savart law for single charges and, as shown here, for currents. Pretty much everything we discussed about electric and magnetic fields up until now could be connected back to these starting points. However, these descriptions of the fields are special cases. Cases where the electric and magnetic fields are time independent or, at most, slowly changing in time. We need a more general starting point to describe other important behaviors of electric and magnetic fields. Fortunately for us, we've already discussed more general expressions for these fields. They are Gauss's law for electric fields and magnetic fields, which, among other things, tells us electric charges can be sources of electric fields, but magnetic fields lack similar such source charges. Additionally, we learned from Faraday's law that time-changing magnetic fields can produce electric fields. There's one more law that we didn't have time to discuss. I'll mention it here. The Maxwell-Ampere's law, which says that both moving electric charges and time-changing electric fields can produce magnetic fields. Together, these equations are known as Maxwell's equations and comprise our most general description of the classical behavior of electric and magnetic fields. One very, very important class of behaviors that we learn from Maxwell's equations that we have not yet discussed in this course is the way electric and magnetic fields can propagate, can travel through space. We have lots of experience with propagating electric and magnetic fields, which we call electromagnetic radiation. Light is one such example. Our very lives depend on the fact that light from the sun can travel to and illuminate our Earth. The backbone of modern communication is electromagnetic radiation. Every time you send a text or stream a movie over Wi-Fi, you are relying on propagating electric and magnetic fields for all that to happen. So, at this point in the course, it's worth spending a little time exploring some fundamental ideas about how that works. To start, let's describe a new way to visualize fields that we will find helpful. Now here we recall that we have typically used arrows at observation locations to visualize fields. Here we use arrows to show how the electric field of a positive point charge behaves at different observation locations. Alternatively, we could draw lines to give us some understanding of how a field behaves. Such lines are called field lines. You draw them in such a way such that everywhere along the line, the arrows representing the field are tangent to those lines. So, for example, here's one such field line. We can repeat this to obtain a visualization like this, which we can then just redraw without the arrows, like this. Now, for this example, we have no propagation of fields. Here we are showing the electrostatic field of a positive point charge. To get radiation, we need that charge to accelerate. So let's look at a glow script visualization of what happens when a charge starts to accelerate. So here we have a positive point charge shown in red here at rest, and the electric field lines showing the electrostatic field. Now, we are going to accelerate the charge briefly downward. And what you see are kinks in the field lines that travel outward away from the accelerating charge. The regions of the kinks represent the places where we have electromagnetic radiation. a pulse of propagating fields. Let's examine this in more detail. So for a positive point charge, the electrostatic field is pointed radially outward as we travel outward along a field line. Thus, at the kink, which happened because the charge briefly accelerated with an acceleration vector A as shown, the field line kink suggests that the E field arrow at that location should point something like this, as shown by the orange arrow. That is perpendicular to the direction of propagation as indicated by the velocity vector v. We can show this is rigorously true for propagating electromagnetic fields by solving Maxwell's equations. Solving those equations is beyond the scope of this course, so we'll just state results here, which in addition tell us that there is a magnetic field B that goes along with the electric field, and that the electric and magnetic fields are perpendicular to each other everywhere, and in addition that the direction of propagation given by the vector v hat is obtained by taking the cross product of the unit vectors e hat and b hat. That means for the specific vectors E and V drawn here, the corresponding B field vector must be out of the page. One more thing to note. Maxwell's equations tell us the propagation speed has a specific value. In empty space, that speed is the speed of light, denoted here with the letter small c and having the value of approximately 3 times 10 to the 8th meters per second. Let's take a look at how all this appears in 3 dimensions. Before we start the simulation, note the yellow arrow shows the direction that we will briefly accelerate the positive charge. We see the radiation pulse travel outward in almost every direction. Notice that the orange electric field arrows and the cyan magnetic field arrows are always perpendicular to one another, and that using the right-hand rule for cross products, we see that E hat cross B hat always points in the direction that the radiation travels. Notice now what happens if we change the sign from a positive charge to a negative charge. For the same acceleration, we see the radiation still propagates outward, but notice the fields point in different directions with E and B still perpendicular and with the propagation direction still given by E hat cross B hat. Now let's put all this on a more quantitative footing by discussing an expression for the radiative electric field of an accelerating point charge. Let's consider an observation location located by the vector r with respect to a point charge q, where, to start, we'll assume q is greater than 0. Let's also assume the charge has an acceleration vector a as shown. Then here's the expression for the vector E sub r, the radiative electric field at the observation location. The constant 1 over 4 pi epsilon naught times minus q divided by c squared times the magnitude of r, all multiplied by a vector that we call a perpendicular, or a perp, which is defined mathematically as shown. Here's what a perp means in words. Take the acceleration vector a and subtract away the component of the acceleration that is parallel to the vector r. You are left with that part of the charge's acceleration that is perpendicular to the vector r. That is vector a perpendicular. Let's sketch it. In this case, a perp looks like this. Now in this case, since q is positive, then our expression for the radiative electric field tells us that that electric field must point in the direction opposite to a perp, because of the minus sign in our expression for vector E sub r. So here's how that looks. Now, the fields radiate away from the charge, so vector v, the propagation velocity, must look like this, and must have magnitude equal to the speed of light, c, in empty space. Moreover, E hat cross B hat are equal to V hat, the direction of the propagation velocity. And since E and B are perpendicular, then the radiative magnetic field must look like this. Into the page. Here's one more result from Maxwell's equations. The ratio of the magnitude of the radiative E field to the magnitude of the radiative B field must be equal to the speed of light, c. So once we have the magnitude of the vector E radiative, vector E sub r, we can find the magnitude of vector B radiative. Let's do a couple of examples. Here we have an electron that is accelerated in the direction shown. At observation location S, what is the direction of the radiated electric field? Stop the video and try to answer this on your own before continuing. First, we sketch vector R to indicate the observation location S with respect to the accelerating charge. We can now sketch in vector A perp. Now, since the accelerated charge is negative, our expression for the radiative electric field tells us the direction of E radiative must be in the same direction as A perp. So the answer to this question is number 8 from the rosette of arrows shown. Here's another example. A proton is accelerated in the direction shown. If we're interested in finding the radiative electric field at observation location S, what is the direction of vector A perp? Stop the video and try to answer on your own before continuing. Notice that when we sketch in the vector R that locates the observation location S with respect to the accelerating charge, we see that vector R and vector A representing the acceleration are parallel. That means A perp must be 0. Therefore, it must be the case that the radiative electric field at observation location S is also 0. Note this happens when the observation location is in the direction or in the opposite direction of the acceleration of the charge. One final point to make. Motion of a charge is not enough to cause radiation. Constant velocity motion of charges produces no radiation. Charges must accelerate in order to radiate. That's it for this lecture. We'll have a bit more to say about electromagnetic radiation in our next lecture.